support that TensorFlow has for mixed precision training. It has quite extensive support for the float16 data type throughout all of its operators. I don't think it's absolutely all the operators, but it seems to be most, and it's increasing all the time. This gives you the opportunity to reduce the memory usage and the bandwidth going into the operators by using float16 tensors. It allows you to improve the compute performance to get speed ups like we've seen using the tensor cores, and just the reduced bandwidth also helps. And so this applies to any matrix multiplications or convolutions that you have in your networks. Should be able to take advantage of this. And we can also maintain the training accuracy by using mixed precision, as Christian has demonstrated for PyTorch. So the steps that we need to take to convert our model, broadly speaking, are the following. To begin with, we're going to just convert the model to FP16, so that'll basically convert the whole thing. And so that'll give us the bandwidth and memory reductions and the compute increase, but we'll have these issues potentially with training convergence. So then we want to add a few tweaks to make sure that the model still converges the same as in FP32 by using mixed precision. So we're going to use float32 for certain operators, just to avoid any potential underflow or overflow. In particular, reductions such as L1, L2 norm, or softmax. The loss is a common example, or range expanding mathematical operators such as the exponential function or power functions can be potentially risky in terms of overflow. So we'll keep those in float32. We're also going to keep the float32 master copy of the weights to avoid these imprecise training updates. As the gradients tend to be small, we want to keep 32-bit weights and apply the small updates, accumulate the small updates into those weights. And we finally will apply some loss scaling to avoid any underflow in the gradients due to the small range of float16 and the small magnitude of the gradients typically. So to begin with the example, so I've got this broken up into some parts. This is essentially the forward model definition part. So just begin with boilerplate up here. And then this is just a simple ConvNet. So we have the inputs being passed into this function, build forward model. We're going to apply a convolution, two-dimensional convolution to the inputs. You'll see I'm using top layer just to represent the current top layer of the network. We're going to have 64 output channels, 7x7 convolution kernel. And we're then going to have a batch norm layer on top of the convolution, followed by a pooling layer. And then we're going to flatten the tensor, and then finally do a fully connected layer, a dense layer, with 128 output channels. And we're going to just return that dense layer. So this defines our simple, basically like a one-layer ConvNet model. And just to highlight the relevant parts for float16, we have the convolution and the dense layer. These are able to use tensor cores, so these are likely to get a lot faster. We have the batch norm that actually will use mixed precision automatically. So the batch norm implementation in TensorFlow will now keep float32 weights, but use float16 activations. We have an example. The max pooling is an example of a layer that doesn't have any, doesn't have a significant performance increase, but it does support float16, so it will get the bandwidth saving and it will avoid having to do any conversion. So this is the second part of the example. This is the part that we'll come back to for changing our model into mixed precision. So the first thing, so this is our building a training model out of our forward model. So the first thing, we're just going to call that the function from the previous slide to build our forward model. We're then going to add another dense layer just to get our logits layer out of the, that is one element for each label in our classification task. So like for ImageNet, this would be 1,000. We're then going to apply a loss on top of this, and we're using a softmax cross-entropy loss. And then we're going to build an optimizer, just a simple momentum optimizer. We're going to call the compute gradients function to compute the gradients in here. And then we're going to apply those gradients to generate the training op. And then we're just going to return all these things that we'll use later to actually perform the training. And this is just the boilerplate code to actually do the training, where I'm just creating placeholders here. I will note that this is not a high-performance model. This is a demonstrative model just to show how to do the mixed precision conversion. The placeholders don't tend to be the fastest way to do things, but I'll use them for simplicity. So we're just calling that build training model function from the previous slide, passing it the inputs and the labels. And then we're creating a TensorFlow session. And we're creating some just random input, initializing all the weights, the variables, and then just doing a simple loop, training loop here, just doing 20 steps, calling sesh.run, and feeding it the inputs and the labels, and then we're evaluating the loss and calling the train op so that this actually applies the weight update. So just an overview, sort of schematic representation of what's going on here. We have the input layer, we have the forward model, which is the function that we defined. This goes to the loss that we compute. And then when we call compute gradients, TensorFlow effectively generates this part for us. It computes the backwards model, and then that will generate the weight gradients, and then we pass, they are what will be used to update the weights. And at the moment, I've represented everything in blue here to indicate that everything is currently float 32. So the first step is that we're going to convert our model to FP16. We're going to convert the whole model. And so to do that, we're going to add a single cast in here. We're just going to cast the inputs to float 16. And that's basically it. At that point, the whole rest of the model will basically infer the type, and they will, if the input is float 16, then the output will be float 16, and so on throughout the model. And this means that the gradients and the variables will also get converted into the float 16. And just showing this schematically, so this is the op that we've added, the cast to float 16 just after the input. And the effect is that this will convert the whole model into float 16. The second step is that we're going to use float 32 to compute the loss. This is one of the sort of mathematically riskier operations, I guess, in terms of float 16. There's a higher chance that we're going to hit an overflow or underflow or precision loss due to the reductions. So we're going to make sure that we do this loss calculation in float 32. And to do that, we're just going to add another cast to cast the logits back to float 32. And so schematically again, this is the cast op that we've just added, just after the forward model and before the loss. And the effect of this is that the loss will get computed in float 32. And then in the backwards pass, TensorFlow will add effectively the inverse of this cast, and it'll cast back to FP16, which means that the backwards and the weights and everything are still in FP16. So we've just made this a float 32 sort of safe operation, but the rest remains float 16. The third step, we're going to convert the weights to a float 32 master copy of the weights. And we're going to do this using a little helper function and the TensorFlow variable scope capabilities, functionality. We're going to wrap, I'll show on the next slide, we're going to wrap a model in a variable scope, and we're going to pass this helper function to that variable scope. And this helper function overrides the mechanism by which TensorFlow will create new variables. So anytime in our model when we call tf.getVariable, a lot of which happens internally in our layer functions, they will go through this function, and this function will just slightly modify the behavior. So the normal behavior would be that this function would get past the d-type in here, and it would create the variable of that d-type and just return that variable. And so instead of that, we're going to just slightly modify it, and the relevant parts I've highlighted here. So we're going to say that the storage data type is float 32 if this is a trainable variable, and otherwise we'll just keep it what it was. So we're only applying this to trainable variables. Non-trainable variables like the global step, we don't want to mess with those. We'll just leave those alone. But trainable, we're effectively going to force the storage type to be float 32 no matter what. We're then just going to call basically back to the original getter function, so just the wrapper. And then we're going to add the cast here. So again, if it's trainable and it wasn't already a float 32, then we're going to cast this to the type that was actually requested. So that, in the FP16 mixed precision case, that would be an FP16 D type here. So we've created the variables as float32, but we're then going to cast to float16. And so that means that we have our master copy in float32, but all the operations will see the cast version as float16. And so in the code that we were looking at, I've added this one line. We've added this TF variable scope here. I've given it a name, FP32 vars. And we're just passing that function in the previous slide, the custom getter, into here. And this just sits around our build forward model function and the logits dense layer. And that's all we had to do. We just move these into this scope. And that means that all the variables that get created in these layers will go through this function and therefore get represented as float32 storage, but cast to float16. And this also means that the gradients are now float32. So they also go through this cast sort of on the backwards pass at the very end after they've been computed, but the computations of the gradients remain in float16. And just to show that schematically, this is the FP32 master weights that we've now imposed, and this is the cast to FP16. And this means that on the backwards pass, the weight gradients come out as float16, but then they go through this inverse cast back to float32, and so we have float32 gradients here being applied to float32 weights, and this is looking pretty much the way we want now. So we've got the key, the forward model part and the backwards model part are all in float16, but we have our safe FP32 loss, and we have our safe FP32 weights, and the gradients will be applied into those. So the last step we're going to apply here is the loss scaling, also known as gradient scaling, I guess. And so what we're going to do here is we're going to define a loss scale value. Here I define it to be 128, so we're sort of shifting by 7 bits. We're going to, before we pass the loss to the compute gradients function, we're just going to scale it up by this loss scale. And then we're going to scale down the resulting gradients. So this returns the gradients upscaled, and then we're just going to do this little list comprehension to do rescale those back to the scale that they were. And so the gradients here at this point are in float32, so it's safe to scale back down. But internally, they were still computed in FP16, which is why we needed we wanted the range shift with the loss scale. So yeah, just highlighting these. So this raises the exponent during the backwards pass, and this returns the gradients to the correct exponent. And again, schematically, we've added this multiply by loss scale just after creating the loss here before we pass to the backwards pass. This then goes through the backwards pass layers in FP16, cast back to FP32, and here's the rescaling that we added of the gradients. And so the effect of this is that now the whole backwards pass is shifted up in range, and so we're going to avoid these underflow issues with very small gradient values represented in float16. And finally, I'll just mention that if you want to add gradient clipping, I think this is somewhat common in certain types of models. It's very easy to add. We have our float32 gradients with the correct scale, so everything's as expected. And we're just calling this TensorFlow clip by global norm function. And this can, in some cases, help improve the quality of the convergence and avoid any numerical issues. And showing this all together, just to highlight the changes that we made. So we had the cast to float16 at the top. We had the cast back to float32 of the before the loss. We had the variable scope to keep the FP32 master copy of weights with our custom getter. We have the loss scaling, scaling up the loss and scaling down the gradients again. And then we have the clip of the gradients at the bottom. And so these 6 or so lines are the only changes that we really needed to make in this case. And this should apply to pretty much most models. This is quite a general approach to converting models in TensorFlow to a mixed precision training